Hello friends, welcome to another lecture of quantum mechanics. Here we're going to show that momentum space wave function is Fourier transform of position space wave function. Okay, so before we start, please subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you. Okay, so if you want to follow me, then this is my Insta ID, ozalukazit123. So now let's start. So now you see momentum space wave function. The momentum space wave function of a wave packet is it can be expressed as phi p comma t. P is nothing but momentum, and this is equal to the Fourier transform of 2 pi h cut from minus infinity to plus infinity. Fourier transformation of position space, that is psi comma t. This is the position space wave function. So we are going to prove this. First let me write the expression. So I by h cut p into x minus e into t dp, right? So here you can see this is nothing but this is Fourier transformation. So I will explain it again. Okay, so here you see this part, this is psi of x comma t. This is nothing but position, this is position space wave function. This is position space wave function, and here p represents momentum and e represents total energy. Right, and so now at t is equal to 0, then it can be written as at t is equal to 0, it can be written as psi naught. So when t is equal to 0, let me rewrite the function psi naught p, which is going to be equal to 1 by root 2 pi h cut, and integration from minus infinity to plus infinity psi x naught at t is equal to 0. So psi naught x, and e to the power, then this part going to be equal to 0 as t is 0, then e to the power I by h cut p into x, right? P into x, that's what we're going to have dp when t is equal to 0. So this is nothing but momentum space wave function, right? So now let me establish this relation. Let me show that this momentum space wave function is the Fourier transformation of the position space wave function. Let me show it. So take the screenshot, pause the video and take the screenshot. Okay, now let me go to a new slide. Okay, and here you see the position space of a wave packet that is given by psi xt 1 by root 2 pi h cut from minus infinity to plus infinity. So here in this expression h cut is not required here. H cut is not required. Okay, from minus infinity to plus infinity. Phi of k e to the power I kx minus omega t dk. Okay, so here the k is, it is wave number. It is nothing but wave number, because when we say wave packet, it's a group of waves, right? So it's wave number, or you can say propagation constant, you can say. So, and here the phi of k, this phi of k is nothing but amplitude of the wave packet, amplitude of the wave packet. Of the wave packet. And how this wave packet formed? Due to superposition of many plane waves. Okay, so that's how it forms. So here you see, first we must know few things here. So, and those are nothing but k is equal to, we must know this relation, momentum by h cut, and this angular frequency omega, that's gonna be equal to E by h cut. So I have considered that you know these things. We know these things will be known to us, right? So in that case, this first one, equation number 1, if you replace the k by this value and omega by this value, then this equation number 1 is going to be equal to psi x comma t. Now we are going to write 2 pi h cut to make it dimensionally correct. So minus infinity to plus infinity. Here phi, here we're going to write pi of p comma t. Sorry, let me write phi of p. So because we are going to replace this k in, by e to the power of, p to the power h cut, e to the power I, here p by h cut minus into x minus omega will be replaced by e by h cut into t, and then it's gonna be dp now in this case. Okay, so here you see, if you simplify this, then you're gonna have 2 pi h cut and integration from minus infinity to plus infinity phi of p e to the power I p by h cut into x. So let me write this way, px by h cut into e to the power here minus I e by h cut here into t dp. That's what we're gonna have. So now let me copy this last step and let me go to a new slide. Okay, so first let me copy this last step. Okay, so here is the new slide. The last step we have got this one. So this one is the last step. Here what we can do, we're going to rearrange these things. So 1 by 2 pi h cut integration from minus infinity to plus infinity with pi of p, we're going to write this term. Okay, so let me write this one with this, and then into e to the power I p into x by h cut here dp. That's what we're going to write. So now this term can be represented by phi of p comma t. Right, here we have time and momentum as well. So what we're going to write here, phi p into e to the power minus I e into t by h cut, that's going to be equal to phi p comma t. So then this wave function in position and space becomes 1 by root 2 pi h cut minus infinity to plus infinity phi p comma t e to the power I p into x by h cut dp. That's what we have got. So now let me copy this and let me go to another slide. Let me take another slide, take the screenshot. Okay, so here is the last step we have got. This is the last step we have got now. So now let me take this as equation number 2. Now by definition of Fourier transformation, So what is the definition of Fourier transformation? Fourier transformation of a function f of x. So also we can represent as this symbol f dash of p. Okay, that is 1 by root 2 pi integration from minus infinity to plus infinity f of x e to the power minus I p x p into x dx. Okay, and let me take this as equation number 3. And inverse Fourier transformation that is equal to, that is f of x, that's going to be equal to 1 by root 2 pi integration minus this f p bar e to the power I, not minus here, it should be plus I p into x dp. So here you see, if you say this carefully, this is suppose equation number 3, sorry, not 3, 4. Now you can see what different different books and different authors used to define this Fourier transformation. They used to write here positive instead of negative. Okay, that's how also they used to define. And when it will be positive, it should be negative. Remember this thing, that doesn't matter which definition you use. If here we have negative sign, it must be positive, and if this is negative, then it must be positive. Remember that. Okay, so that's how we used to define Fourier transformation. So now you see, if you compare this equation number 2 and 4, so if you compare equation number 2 and 4, just let me rearrange these things, just wait. Now here you see, comparing 2 and 4, here you can see, in this case, this f of p bar is, in this case, nothing but phi of p comma t, right? We can compare with this, right? And we can compare this f of x as this, and we can compare f of x as psi of x comma t, right? And if we do so, then here we can say that this part, here you can see, this is now inverse Fourier transformation of this. So if that is the case, then if we write this equation number 2 in this form, we have to change this to minus, right? And this should be written here, and that should be written there. So here we can say that this one, your inverse transformation, inverse Fourier transformation of phi of p comma t is psi of x comma t, psi x comma t, right? So therefore what we can write, so let me take a new slide. Okay, so what we're gonna do here, we're gonna replace we're gonna if this is the inverse, if the inverse Fourier transformation of this is this, right? So then we can write this one in this form. How? Let me tell you. Just now here you see this term is now this one, and this is this one, right? So if we want to write this equation in this form, right, then what we can write is that this one will be this one, that is your phi p comma t, and this one will be that one. This f of x is nothing but here psi of x comma t, psi of x comma t, and this dp, this dp will be replaced by dx. This dp will be replaced by dx, right? So hope you have understood this. So what we can do now, so equation number 2 implies, therefore equation number 2 implies, let me copy this equation number 2. So let me go to a new slide. So here you see this was the equation number 2. Let me make it smaller. This was equation number 2, right? So here what we are getting, this one is inverse Fourier transformation of this, right? Inverse Fourier transformation of this is phi x comma t. So therefore we can write equation number 2 implies that phi of p comma t, which is the wave function in momentum space, is nothing but Fourier transformation of root over 2 pi h cut from minus infinity to plus infinity, here psi x comma t e to the power, now there was positive, so it's going to be negative now in this case, as we have taken Fourier transformation p of p into x h cut. So this is p into x by h cut, here we're going to write dx, right? So this is what we have got, right? So now just wait, this is minus infinity, so that is what we have got. So now let me clean this equation as we have already written earlier. So now you see, if you compare this equation with equation number 3, I think let me go back to previous slide. If you compare this one with this equation, so let me copy this equation, and let me rewrite it on the new slide. So here you see this was the equation. If you compare this equation, this is your momentum space wave function, and this one is the f of x. So this is what Fourier transformation of f of x, that means Fourier transformation of this one. So we can say this is equal to Fourier transformation of psi of x comma t, right? So comparing with equation number 3, this is suppose equation number, so last equation was equation number 4, now equation number 5. So comparing 3 and 5, we can say or we can simply this momentum space wave function is nothing but Fourier transformation of position space wave function. So therefore momentum space wave function is Fourier transformation of or Fourier transform of position space wave function. Right. So hope you have understood this. If you think this video is helpful, then please do share with your friends. Inspire me to create new contents for you and stay connected.